Here we have two geometric problems. Here's the first, and here's the second, involving proving an inequality based off the diagram we have there. So let's go through the first one. So suppose there are 5 points inside some square with sides of length 2. We need to show that there must be 2 of these points within root 2 units of each other. So let's start by drawing out the scenario. So let's see if I can draw a nice square. And so we have that the square has a side length of 2, 2, 2, 2, 2. So we need to put 5 points inside this square. So let's say we have a point here, 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 here. And then to attempt to disprove this, the statement that two of these points are within root 2 units of each other, we could try to space out these points by placing the fifth and final point in the middle to try to centralize it and maximize the distance away from the other 4 points. However, we come across an issue where if we look at the middle point and consider the distance between that point and any other point, say if we even wanted to extend the distance of this point here to the boundary, to the corner, well, that distance is going to be exactly root 2. If you consider that distance there, and let's figure out why that is. So I'm going to subdivide this square into quadrants. It's not very good. It's good enough. And notice that when we do this, for each of the smaller squares, the side length is 1. And if you take the length of the diagonal, using the Pythagorean theorem, we get that this length is the square root of 2. So if you plot any 4 points, say if we try to use that technique I mentioned earlier, where we try to space out the 4 points as much as we can, placing them one in each of the smaller squares, we notice that when we insert the 5th point, it either is in the middle or along these 2 lines. So let's place it in the middle, and if you take the distance between that point and any other point, because the length of the diagonal of the unit square is root 2, then the distance between that center point and any other point is within root 2, because root 2 is the max length from the center to any other point in the unit square. Okay. So let's just take these points out. Okay, let's I guess show this in writing. So first, what we want to do is plot 4 points in the square. such that each of the unit squares, so each smaller square contains a point. Okay. So we're actually relying on a principle here called the pigeonhole principle. So I'll write down what it is. So the pigeonhole principle. So basically what it says is if you have n number of objects, if n objects are placed into m number of containers, so in our specific case, a container is one of those unit squares, but more abstractly we call them containers. And of course we have that the number of objects is greater than the number of containers, so with n greater than m, then at least one container must contain more than one object. This is a principle that's stated more formally here. It is quite common sense if you have, say you have 3 pigeonholes here, 1, 2, 3, you have 4 things to place those things into, and you want to place them into these containers. The constraint of the number of these containers here forces at least one of the containers to contain more than one, so at least 2 objects. And that principle generalizes this example. Okay, so that's the pigeonhole principle. So from here, we can say that by the let's just say that by the pigeonhole principle, we have that the 5th point must be in a smaller square with another point. Okay, so as I've shown earlier, when I tried to place a 5th point as far away as I could from the other 4 points, I found that 5th point had to be shared in one of the unit squares with another point. So 2 points had to share a unit square, sorry. Okay, so the maximum distance between these 2 points inside that unit square is the length of the diagonal. So it's root 2. Pythagoras. So I'm not going to write anymore. It's pretty clear that so we've shown that that 2 of these points are within root 2 units of each other. There could be more, but there must be 2 of these points that share the space of a unit square. Okay. There we have that. And then for the next one, we have a diagram here. We have 2 circles, one larger, one smaller, with they're kind of rolled up next to each other. And we want to prove that a plus b over 2 is greater than or equal to the square root of the product of a and b. And we can assume that a is not equal to 2b, even though it looks like that in the diagram, but it could be, but in general it is not the case. Okay. So what do we do to create some sort of inequality or equality, and then then from there we can try to see what proportion is greater than the other, and so on. Okay, let's just make some stuff up. Let's just play around with it. So I could kind of manipulate this this diagram, not manipulate it, but I guess scribble or graffiti on it. I can notice that here I could generate a right-angled triangle. Well, that's no good. Yeah, that's good enough. So I'm coming from the center of the smaller circle, extending out a line horizontally to the left until it meets the vertical point of the center of the larger circle. Okay, so let's label the sides of this right-angled triangle, x, y, and the hypotenuse with h. And let's label the corners of this triangle alpha, beta, and gamma. Okay, so let's just make up some equations here. So straight away, I know that, well, I could find an expression for h. So h is, well, it's this distance plus this distance, and the first distance is just the radius of the larger circle. And because the diameter of the larger circle is a, the radius is going to be a over 2. And so with that, we have to add the radius of the smaller circle. In the same way, the diameter of that smaller circle is b, hence the radius is going to be half of b. And so when we add these up, we get a plus b over 2. Okay. So we have an expression for h. We can find an expression for x as well. So that's h x. So what can we do for x? Oh yes, so what we have for x is an expression here, a over 2. Instead of adding b over 2, we're minusing b over 2. So this distance here is x. So what is a over 2? A over 2 is this distance. B over 2 is this distance. And so if we subtract this distance from this distance, we get x, which is left over there. Okay, so we have a over 2 minus b over 2. Simplifying that, we get a minus b over 2. Okay. So we have expressions for h and x, and also by the Pythagorean theorem, we get that the sum of the squares of x and y, let's write it out here, so x squared plus y squared is the square of the hypotenuse, which we don't, let's just write as h for now. X squared plus y squared is h squared. And let's get y on its own. So y equals the square root of h squared minus x squared. And we have expressions for h and x. Let's put them in. So h is a plus b over 2 squared. Subtract x squared, which is a minus b over 2 squared. Simplifying further, we get the square root of, let's take a common denominator of 4. So we have the sum of a and b squared, subtracting the difference of a and b squared. Taking out the square root of 4 in the denominator, we get half a plus b squared minus a minus b squared. It's going to get a little boring, but let's expand this. So you get a squared plus 2ab plus b squared, and then we're minusing a squared minus 2ab plus b squared. And notice that the squared terms cancel out, and we're left with half. So we have the square root of 4ab, which is just the square root of a times b. Okay, so we have an equality here. We want to show this. So we have that expression root a times b. But how do we force an inequality here? So let's think of something that we know. Well, let's look at the triangle alpha, beta, gamma, the one I've drawn up here. So note, since, well, that triangle, the way we've drawn it up, it's right angled. And because it's right angled, the hypotenuse is greater than or equal to any of either of x or y. So since it's right angled, we say that the hypotenuse length is greater than or equal to y. Well, the reason I've chosen this inequality is because we have an expression for h, which is a plus b over 2. And we have an expression for y, which is root ab. And there you have it. So those are two geometric problems of different sorts.